Okay, you have this function, and you want to maximize it or minimize it along this curve. That curve's a straight line in this case, but in general it's going to be a curve, right? In other words, subject to this constraint, subject to just points where x and y satisfy whatever this is, this has to be equal to 4, okay? You want to find points where this thing is a maximum or a minimum. Well, first of all, we note that the gradient of f is the direction of maximum increase, okay? And correlated with that, as we mentioned in class last time, direction of no increase or decrease is perpendicular to this, right? Okay? So what we want to do, now I'm not going to realistically graph the gradient of this thing, although there's a paraboloid here and the direction of the gradient is fairly obvious, okay? It's actually pretty much straight away from the origin, if I've got that one visualized right. And it's just a rotated circle, which in any plane, which means it's a circle. You know, you rotate a circle, it doesn't change. If I'm visualizing it right, I think I am. So actually, I know where your gradients are here, just geometrically, okay? And they go like this, straight away from the origin. So these are your gradients at various points. Where is your gradient going to be perpendicular to this curve? Well, the way I've drawn it, it's going to be like, you know, just take a perpendicular back to the origin. Now, I didn't draw it accurately, okay, because the slope is only like -2/5, right? So it's more like this, so it's going to be at a point more in this direction from the origin. But you get the idea that here's your bingo point, okay? Here's your point, and this is just a depiction. It's not an accurate graph of this function, okay? That makes sense? So the gradient is perpendicular to your constraint curve. So rate of change along the curve is 0. Okay? Pretty much a critical point. That intuitively makes some sense. If you understand the gradient as showing you the direction of maximum increase, then it's easy enough to prove that perpendicular to that is the rate of no increase. Your directional derivative perpendicular to the direction of the gradient has to be 0.
How does that paraboloid even have a direction of max increase?
Well, in what direction? Okay, imagine a paraboloid here, right?
It's a circular.
Now, in what direction do you move in the direction in the xy plane to climb the paraboloid most quickly? Well, you move straight away from the origin. Unless my geometric intuition is totally screwed up, which might be, you know, this time of the day. Okay?
You could move at any angle from the
No,
origin.
no. Okay, here's your paraboloid. It's curving above us right here, right? So it's like you're climbing this paraboloid. Okay? If you move straight away from the z-axis, that's where you're climbing most quickly. Or if this is a slide, you sit on the thing, you're going to slide toward the z-axis. You're going to slide down toward the origin. That's where you're going to end up. Okay? So think about that. Seems pretty obvious to me right now, and I'm not going to write out the proof, although the proof is pretty easy to write out. I mean, yeah, we can take the gradient. What's a gradient? 2xi plus 2y, 2x plus 2yi, right? And 2x plus 2yj. Okay? Well, that's just 2 times the quantity x plus y times I. Okay? And it seems that the gradient is always then at 45 degrees, which kind of contradicts what I was saying, so I'll probably have to write that out and make sure. Because I'm pretty sure my intuition's correct. Okay? By the symmetry of the situation, that has to be so. Anyhow, we're speculating. Let's get back to not the specifics of this situation, which we can address in a minute, but the idea that your gradient needs to be perpendicular to this constraint curve. Okay? And your constraint's always going to be something that gives you a straight line or curve in the xy plane. Okay? So that's where we are. Now let's see where that leads us, because what we want to do now is we want to regard the constraint as a level surface of this function. Okay? And we want to talk about how that works and why that works out.